insulator that can separate charge. And so if you're going to make a battery, in a sense that's a battery. So you've got a plus and a minus pole on this battery. And you've got an insulator that keeps the charges from coming together normally. And so now you've got a situation set up, you can harvest some energy. You've got a battery, you can do something with this. Well, what are you going to do with it? Well, how about use it to transmit a nerve impulse? And I love this part. Years ago, okay, I used to tell my students, it's like there's a donut-shaped protein. And donuts are one of my favorite subjects anyway. There's a donut-shaped protein in the membrane with a little lid over the hole. And that lid normally keeps sodium and potassium. It's too closed to let sodium and potassium through. And it's really the surplus positive charges that kind of keep it, fairly tightly sealed so the sodium and potassium can't get through. Well, I was just using it as a teaching model. Guess what? They found out there really are donut-shaped proteins that really do have a little lid on them. And so what happens is you need something to trigger it. You got to open one of these sodium gates, they're called. And so that's usually something like acetylcholine. A nerve can dump this chemical on it, and the chemical acts like a little grabber that grabs a door, by the handle and pries the door open. Well, when the door opens, now sodium and potassium are sized appropriately to move through that opening. Who goes first? Well, you can hear the argument. Sodium says, you go first. No, you go first. So like Laurel and Hardy, they're both going to try to go through. No, you think on the basis of diffusion, you'd say, well, potassium would go first because it's got a 14 times gradient. It would diffuse out before sodium would diffuse in. But then somebody else would say, well, wait a minute, potassium's bigger, it would diffuse slower. And then they say, well, sodium is smaller, but it holds 2 shields of hydrogen water molecules around it. So its diffusion weight is about the same as potassium. And so now you're back to potassium going out first, except what? It's plus on the outside, minus on the inside. So in addition to the straight diffusion gradient based on molecular size and concentration difference, there's an electrical gradient. And so the result is sodium goes in first. And so sodium and potassium diffuse at approximately the same rate. Potassium ought to go first, but because of the electrical gradient, sodium goes first. On average, of course, in reality, there are trading places like that. But on average, more sodium comes in. Well, what does that do? That wipes out the electrical gradient that allowed them to go first in the first place. And so now potassium, with its greater diffusion difference and comparable hydrated size, goes out. What does that do? That reestablishes the plus charges on the outside, closes the gate. And so that's the basic event in a nerve impulse. It's a little pulse. And so you have a polarized membrane, plus pole and a minus pole. And then you pry open the lid, you have a depolarization. The plus charges rush in and neutralize the net negative charge, and then some plus charges rush out, reestablish the plus charge, and close the lid. But before they do that, that would just be a flick up and down. But there's another sodium gate over here at, guess what, just the right distance. Okay, with its lid closed, because it wasn't stimulated by that chemical. But when the plus charges flow in at this point, the plus charges holding this one closed diffuse toward the first pore, so it opens up. So as this one is repolarizing, stopping the impulse, this one's depolarizing, continuing the impulse. And so a nerve impulse is carried kind of like a spark traveling down a fuse. And so you set fire to the fuse, and that fire lights the next part of the fuse, lights the next part of the fuse, lights the next part of the fuse, and so the spark travels down the fuse. But a nerve membrane is alive, and so it's different from the fuse. You light the fuse, and the spark travels down, and the living membrane rebuilds the fuse. So there's just a little spark, and a new fuse coming along right behind it. So you get a wave of depolarization followed by repolarization. And the diffusion is phenomenal. It takes advantage of the hydrated size of the particles, the diffusion concentration differences. The net result of that, by the way, is that the transmission of a nerve impulse takes virtually no energy whatsoever. What's the bad news? You can think, and you can think, and you can think, and you can study for exams, and you can't lose a pound. It's just not fair. You walk around the block, you burn no energy. You think like crazy and nothing, all the energy of studying for final exams is in half a peanut. Okay. Now, in a way, that's a little bit unfair because the brain and the nervous system has high standby energy. And so it actually does take a lot of energy to keep the brain and the nerves alive, but you have that anyway. And so all that extra thinking you do is burning no additional energy, or too small to measure. And the number of molecules that trade places, are just, well, the number's high, but the percentage is extremely small. And so a given nerve impulse can carry, the typical nerve, now it varies with the individuals, but can carry hundreds or even thousands of impulses before so much sodium and potassium have traded place that the pump has to recharge the membrane. Normally you would never get to that point. You'd have to deliberately, overstimulate a nerve to ever get to that point. And so it's just phenomenal. Diffusion works all the way along the way at multiple points to make a system work. So the evolutionists would say, see, I told you so. It's all a matter of chaotic motion. And the average person, the average thinking person, the creator would say, what are you talking about? Just a random diffusion of sodium and potassium isn't going to do any of that. You have to have all that structure and all that spacing and all that size difference and all of that, has to be set up ahead of time before you can use that otherwise random. Again, sodium doesn't say, oops, it's time for a nerve impulse. I got to hurry. Pardon me, I got to go in. Now it's my, no, they're just bouncing around at random and responding to the local conditions. But the system has been designed to generate this phenomenally coordinated event. So again, it's the system that gets the credit and the designer of the system, not the random chaotic.